This is the third red teaming exercise, and in this exercise we're going to be focusing on virtualization and softwarization in the context of 6G network security. So again, this is a red teaming scenario exercise. It's the third one. Let's look at the first two in case. So the first one was AI security risk assessment in cloud and edge and AI in 6G network trust infrastructures. That was the first video. The second was AI supply chain risk analysis scenario demonstrating the distributed AI and machine learning in 6G environments. And now we're in the third scenario. So here we're again applying red teaming exercises, but in different contexts. So what is the expected research outcome from this exercise? What are we trying to learn? We're trying to learn and to understand how softwarization and virtualization creates new threat surfaces, specifically in 6G. We're trying to apply red teaming methodology to hypervisors, CNFs, and orchestration APIs. And third outcome that we're trying to learn is evaluate the AI-based trust system in dynamic and adversarial multi-tenant environments. Now, again, as with the previous two scenarios, I'm gonna go quickly through this scenario on the computer, and then I'm gonna shift and I'm gonna use the iPad to be drawing connections between this and to explain how the scenario works. And after explaining the scenario, at the very end, I'm gonna come back and I'm gonna explain how the scenario was developed. But as a brief guidance point, when we build scenarios on technologies that they don't exist, like 6G, we use existing literature and experts in the field. One of my very recent examples that the scenarios that I built included 750 different research papers. So once you evaluate all the recent literature on this topic, once you study all the conferences and all the material that is available on Web of Science, on Scopus, on Google Scholar, and you develop the scenario that needs to be based on established knowledge. So it's not just boxes that I tick or my opinions. Every section of this diagram is going to be referenced in the final slide, in the final presentation. So this is just the video. It will be presented probably on a conference or in a journal paper, but the problem is with conferences and journal papers, there's a peer review delay, so it might be 6 months after. Let's look at the scenario. So we're going to be looking at hypervisor drift and how to convert lateral movement to virtualized 6G network functions. And this is the scenario that we are building. Then we're going to have a red teaming intelligence leak. So we have an advanced persistent threat actor has developed a covert virtualization layer exploiting targeted unpatched KVM hosts in edge POP point of presence. The API achieves the algorithmic red teaming exercise would achieve 4 objectives, and those are the 4 objectives here. And we're going to be conducting vulnerability focused risk analysis and red teaming plan. We're going to build a red teaming plan. And again, as with previous scenarios, we're going to have steps. For this step, we're going to be using the MITRE, ATLAS, and the STRIDE. Then we're going to have attack simulations, and we're going to be looking at AI augmented defense reviews. Then we're going to have the risk table. As with scenario 2, scenario 3 would also have a risk table. And we're going to devise some blue team countermeasures. I know that the red team works on identifying the vulnerabilities, but also we need to sometimes look at those, how the solution would look. And because that is required for the testing. What kind of testing do we propose? And in order to validate that those vulnerabilities are actually vulnerabilities, we need to ask specific questions. So what is the problem? We put that in a question, we test the question, and that is the entire exercise here. So now I'm going to shift to the iPad. Let me close this. And I'm just screen sharing my iPad screen. Now you should be able to see the same diagram, but in the iPad. And for this one, I'm going to be using a different cover pen. So let's see what cover should I use. For this one, let's pick this one. Spectrum slides, okay. Maximum, fine. So let's go quickly through the scenario, through all the boxes that are developed here, and then I'm going to explain how the scenario was developed. But first, let's understand the scenario, because that's the most important. I have already given you the explanation that scenario is built based on existing literature and knowledge from various different conference papers and journal papers that they emerged in the last 12 months. So first, simulator stimulation, we're looking at hypervisor drift and convert layer movement virtualized 6G network function. So the 6G network deployment of a fully virtualized disaggregated ratio access network, so that's the abbreviation, is based on 4 key technologies. Number 1, software-defined networking. Number 2, network-defined network function virtualization. Number 3, containerized apps for ORAN intelligence controllers. And number 4, multi-tenant hypervisor running at the run node and core cloud modules. Those 4 key technologies would lead to the system dynamically instantiating the VNFs and the CNFs. Those are the containerized network functions across a distributed infrastructure to optimize latency, energy use, and network load. Now, the security posture in this scenario is based on the following 3 criteria. So first one, standard virtualization isolation models. 2, the secure boot and remote attestation, which is limited to the control nodes. And 3, the basic host and container level monitoring. Hold on, just 1 second. I thought my phone was ringing, but it's not ringing, just imagination. Nobody's calling me, nobody needs me. So the red teaming intelligence leak, we have an advanced persistent threat actor that has developed a covert virtualization layer to exploit targeting unpatched KVMs hosts in edge point of presence. So this advanced persistent threat is trying to achieve these 4 key objectives. It's to escape from containerized network function to underlying hosts. Second, the persistence with side loading, KEMU, image manipulation. And third is command and control tunneling using east-west traffic distinguished as legitimate VNF telemetry. And fourth is micro-segmentation bypass by mimicking trust marks of softwarized orchestration agents. And this is a lesson for me to never put text in that, because you cannot really read it properly. But what does it do? This creates a hypervisor drift zone, an invisible threat surface where the attacker can deploy synthetic VNFs instances to exfiltrate data, to launch spoofing attacks, or silently disable anomaly detection engines. What are we going to do about this scenario? How would you address? Let's say this is a realistic scenario and it happens to you in your company. Well, virtualization focused risk analysis and red teaming plan. That's the first step, that we need to make the plan, and the plan needs to be virtualization focused risk analysis. Number 1 step would be softwarization threat modeling. So you would use the stride or MITRE attack for containing the identity. You could analyze threat actors, so external, and internal supply chain vendors, for example, that could also be in the list. You need to assess the exploitable layers, the hypervisor, the container runtime, the orchestration plane, and you need to look at the attack goals. Why would they do this? To extract data, for data exfiltration, disruption, or stealth persistence. When you're building this kind of strategies, you need to focus on lateral movement across softwarized services, API abuse and orchestration tools like OpenShift, Kubernetes, and you need to look at the exploitation of shared resources like SRIOV misconfigurations. That's the first step. The step number 2 would be attack stimulation plan. So you need to design a red teaming campaign to target the virtualization stack of the 6G edge cluster. So here we have 4 steps. Step number 1 would be initial access via compromised VNF lifecycle manager. Second step, exploitation, CV linked escape from sandbox to host. So that's another one. Third, lateral movement via SDN, rule tampering, or fake service mesh telemetry. Fourth would be persistence. So convert site loading or tampering into the REC with valid telemetry signatures. When you're analyzing those, you need to be documenting the following things. So the entry vector, the privilege escalation path, the obfuscation strategy, and the exfiltration technique. Those things need to be documented. Step number 4, AI augmented defense review to assess the role of AI and machine learning in detection and orchestration. So the question here is, can the model-based anomaly detection distinguish between real and synthetic CNFs? Is the AI trust scoring engine itself vulnerable to poisoning or mimicry? Are the models updates securely delivered, validated, or monitored? Those are the things that you need to have in this defense review. So those are the questions that you need to answer. And then you can build a virtualization risk table, like in the scenario 2. So here you would have slightly different structure, but then the structure depends on what are your priorities. In this scenario, I would be looking at layer, vulnerability, threat actor capability, the impact, and detection difficulty. So for a layer, is it the hypervisor? Is it the VNF scheduler? Is it the SDN control layer? Is it the app manager? And in terms of vulnerability, they would be specific to specific layer. So in this first layer would be unpatched kernel, exposed management interface. In the second layer would be API abuse, inefficient authentication, for example. In the third layer, it could be misconfigured flow rules, poison telemetry. And in the fourth layer could be insecure supply chain or update validation. Then you need to assess the threat actor capability. Who is the threat actor? Is it the high, medium, high, or low? So if the actor doesn't have the capability to influence that, then it's less concerning. But if the actor has a high capability to perform those, to exploit those vulnerabilities, then you have a problem. And if you do have a problem, what is the impact from that problem? Well, it could be host compromise, VNF impersonation. What is the detection difficulty of that? It's low, for example. Another impact for the second layer would be rogue VNN instantiation. Let's say the difficulty is medium. For the third layer, lateral movement traffic hijack. And then you have the detection difficulty, how difficult it is to detect that. And the fourth layer, deployment of malicious apps. So if it's deployed, how likely is to detect? Well, detection difficulty is high, so the detection is very low of this one. That's why you need to be careful before you put those in there. Step number 5. These exercises are getting slightly long. One exercise per day is enough. Third exercise for today that I'm doing. Step 5, blue team countermeasures. So here in the blue team countermeasures, you need to brief on defending softwarized 6G infrastructure. So how do you defend this? That's what the blue team does. So you can recommend, for example, hypervision, isolation, validation via continuous attestation and eBPF hooks. Second would be runtime CNF scanning using AI-enhanced behavioral profiling. Third would be zero trust orchestration plane, mutual TLS short-lived API tokens, context-aware deployment policies. And last one would be synthetic model injection testing. So red team injects adversarial X apps to test blue team detection. So it's kind of like a game. And this testing, the final step, how would that done? Well, again, it's important to ask yourself a question, or to ask the group of people who are testing it a question. If a VNF in a 6G edge cluster is behaving suspiciously, but has a valid trust signature, should it be shut down? What would your automated red-blue playbook do? So what is going to be the response to that? And to build the response, here's the steps. You design an AI-assisted decision tree, integrating real-time risk scoring, model-based trust indication, policy-driven automation mitigation, and human-in-the-loop escalation triggers. So that is the actual scenario that we have over here. Now let me change the cover into something different. Let me go to the grid and pick blue. No, let's book red, so it's or green, to be different from the existing cover. That's what I was looking just. So let's look at how this scenario was created, because now we have listed the scenario, and you know, if you're watching this video, you're thinking, yes, but how did you come up with those, and why do you think those are the most important criteria? Well, I'm not going to list you all the 700 plus references that there, because that's going to take way too long. You're going to have to read the conference paper, and in the conference paper you would have all those references. They're going to be included there. The red teaming virtualized AI inference environment in Softwarised 6G network. The scenario, it tests the model robustness and the inference integrity in a virtualized environment. So this provides a simulation of how an attacker would exploit weaknesses in containerized and orchestrated AI deployment. And when we are looking at visualization and softwarization attack map, well, this whole process here is basically building the attack map and explaining how that would work. But let's walk through this process that we just described. How was it built? We're looking at AI system deployed in virtualized 6G network environments. So AI system deployed in virtualized 6G network. What you would see here is realistic attack diagram that is presented, but the maps are compromising the application layer to the hypervisor and act across the lateral orchestration paths. So it's very specific. So how did we get that? Well, first we looked at entry points. So hold on. Did we get? No. The attack begins with the VNF lifecycle manager VPN. So this is exposed because of misconfigured authentication. The attacker would exploit this inference to upload a tainted container image camouflaged as a legitimate AI microservice, and specifically an X app responsible for network anomaly detection. The second step would be the CNF escape and host privilege escalation. So that is the second part of this scenario, because once deployed, the malicious X app executes a container breakout using a known kernel exploit, for example, a CVE exploit. Then it reaches the underlying host OS and achieves root access and bypasses the soft compartmentalization. So this is the first red flag. CNFs and VNF need kernel hardening, not just runtime firewall. That's what we learn from this exercise, that we need to have kernel hardening and not just runtime firewall. Then we move to east-west movement with the SDN rule injection. And this is again referring to the VNF and CNF, which are containerized network functions. So just to, maybe I should use that as opposed to VNFs and CNF. But so with access to the host and visibility into the neighboring VNFs, the attacker then rewrites this SDN flow rules with the orchestration agent, and this creates a covert command and control channel across the lateral 6G edge nodes. It's disguised as a trusted telemetry between XApps, and that mimics legitimate network function communications. So fourth, and here we're slowly moving all the way to CAMU, persistent reconnaissance with drift hypervisor state, because this is the clever part, because rather than exfiltrating the data outright, the attacker modifies the CAMU VM image on the edge hosted to embed persistent low noise backdoor, and this is what we call hypervisor drift. No one notices because everything above the AI orchestration, SDN, and even the monitoring agent continues to report all green. Then we move to the trust supervision of AI orchestration layer. And at this stage, the attacker poisons the input fed into the AI-based trust scoring system, and they control which flow gets flagged as malicious, allowing specific traffic types to pass undetected. Because the AI model is trained on operational data, which is now manipulated, it begins to trust the attacker synthetic XAP. And here we need to maybe end this with a few discussion points. Let's analyze this scenario through AI retheming lens. Which layer would you prioritize hardening? The model, so the container, or the orchestration layer? So those are your choices, but which one would you prioritize hardening? And you need to go back to the video, watch it from the beginning, and then the answer is going to be there. But just asking this as a question because sometimes these demos can be slightly difficult to understand, and I just want you to, I'm asking you this question to make sure that you actually understand. So which layer would you prioritize hardening? Which layer would you harden? The model, the container runtime, or the orchestration layer? Let me ask you a second question. So can the model explainability of SHAP techniques help us detect telemetry-based C2 activity? That's a question. So would that model explainability techniques help us detect telemetry-based C2 activity? Final question, how do we build real-time trust anchors when the orchestration layer is softwarized and dynamic? So the anchors are static and the layer is dynamic. But those are the questions that you need to... Storage is almost full. Oh, okay, so thank you. Those are the questions that you need to ask yourself. Hold on, let me see if I can new movie recording. Because the questions determine your knowledge about the process. If you cannot answer those questions, it's best to rewatch the video again, and then once you rewatch the video again with a focus on the actual question, hopefully it's going to become clearer. But this is just a demo. Actually, and the benefit of video is that it's fast. The benefit of this diagram is that it's fast. But when you read the actual conference paper, the conference paper is going to be peer reviewed. That means it's going to be sent to 2 different experts in this area, and they will detect weaknesses. So this is just what I found, but maybe some of these things here are in error. The conference paper probably won't, it hasn't finished and it hasn't been submitted. I don't even know which conference is going to be submitted. So the conference paper is probably going to come much later. And the final scenario might even look slightly different than this, because it depends on the peer review. If they spot weaknesses, those will be corrected. But that's another reason why you should read more conference papers. See you in the next video.